In this segment, we'll be talking about graphing equations, and here's the equation we'll start with. It's a linear equation involving two unknowns. We're going to use the point plotting method here. There are several methods for graphing. Point plotting is a rather fundamental one. It is, however, the one that's used in your graphing calculator, which we'll look at a little bit later. At any rate, the notion of point plotting is related to the idea of solution. Now, the solution to an equation like this is a value of the variable or variables, as we have here, that will cause the statement of equality to be true. If x is 2, for example, and y is 1, then we have a solution pair. If x is 2 and y is 1, then let's see what happens. We would have negative 2 times 2, that's negative 4. Then if y is 1, we have plus 1. Negative 4 plus 1, that's negative 3. Negative 3 is equal to negative 3. Yes, that's true. So this ordered pair makes that statement true, and therefore this is a solution to that equation. The whole idea of point plotting is to find solution points and plot them on a coordinate plane. Now, to find the solution points, we make a table of values like this, a table of x and y values that solve this, and we set up the table like this, and we select at random values for one of the letters, and then we solve for the other one in the equation. Now, an easy way to do that is to take the equation and to solve the equation for one letter or the other. This equation is pretty easy to solve for y. If I add 2x on both sides, I have y equals 2x minus 3. Now I can use this version of the equation to complete my table of values. Let's let x take on values, let's say negative 2, 0, 2, 4. And to complete the table, I simply replace x with these values, solve for y, and away we go. If x is negative 2, we have 2 times negative 2, that's negative 4. Negative 4 with negative 3 is negative 7. If x is 0, this term goes out, so y is negative 3. If x is 2, 2 times 2, 4. 4 minus 3, 1. If x is 4, 2 times 4, 8, minus 3, 5. Now let's plot these points. The point negative 2, negative 7, that's negative 2, down 1, 2, 3, 4, 5, 6, 7. And 0, negative 3, 2, 1, 4, 5, and the graph contains these points. Notice that the points are collinear. That's always true with a linear equation. The graph will be a straight line. The points on the line then are collinear. And because of that, I guess we don't need to plot this many points if we're constructing the graph of a linear equation. We only need really 2 points, but for verification purposes, you might tack on a couple more. As equations become more and more complicated, though, their graphs become more and more curvy, so you have to plot more and more points in order to discover the behavior of the graph. The most important relationship between a graph and its equation is the idea that the graph is truly a picture of the entire solution set for that equation. That is, if we take any point on this graph, it has associated with it coordinates, x, y. And these coordinates, when put back into the equation, will make the equation true. So for every point on the line, we have a solution associated with the equation. That's a very nice kind of relationship that we'll come back to quite often. There are some aspects of graphs that can help us in constructing graphs and in noticing certain characteristics about equations and graphs and the relationships between them. The first idea we'll talk about in that regard is intercepts. Now, intercepts are the places where the graph crosses the x and y axis. X-intercept is the place where the graph crosses the x-axis. Y-intercept is the place where the graph crosses the y-axis. Now, to find x and y intercepts, we can simply, if we have the graph, we simply look at the graph. Now, and we're going to do this both ways. That is, we're going to identify x and y intercepts both algebraically and by just looking at the graph. X-intercept G, it's about right here. You see, the place where it crosses the x-axis. We don't know the exact spot because it's not an integer value, but it's in that neighborhood. The y-intercept is exactly right here. It's at negative 3. Now, a lot of times we want to use x and y intercepts in the construction of the graph. That is, we want to calculate the x and y intercepts and actually plot them as a couple of points on the graph. Now, let me tell you conceptually how that's accomplished. It should make some sense that suppose we don't know where the graph crosses. Suppose that we eliminate the graph. I'll just take it off here. We don't know where the graph is. We don't know how it behaves in the coordinate plane. It may be really curvy, may be a straight line as this one is. We don't know anything about it. But we do know this. We know some characteristics about intercepts. That is, we know that for any point on this x-axis, that the coordinates of that point are some value of x, but the y component is 0. And if the crossing happened to be out here, no big deal. The same characteristic exists. We have coordinates. The x component is something. The y component is going to be 0. Now that tips us off as to how we find x-intercepts. We find x-intercepts by letting y take on the value 0 and then solving for x. So up here for the x-intercept, we let y be 0 and solve for x. If we're talking about the equation we just looked at, I'll use the original form of the equation. It's negative 2x plus y equals negative 3. And if we let y be 0, we have negative 2x plus 0 equals negative 3. And now it's fairly easy to solve for x. We divide on both sides by negative 2 to find x to be 3 over 2, which is 1.5. You see, and then we could actually plot that point. Now that's the point, 1.5, 0, so that point was right here. Okay, so the x-intercept is the point 3/2, 0. All right, for the y-intercept, it's the same idea. That is, the concept for finding the y-intercept is very similar. We may not know where the graph crosses the y-axis, but for every point on the y-axis, the prevailing characteristic is that the x-coordinate for all these points would be 0. And we don't know what the y is, that's what we're looking for. But the idea that the x component is always 0 tips us off as to what we do. To find the y-intercept, we let x equal 0 and solve for y. All right, let's do that. We have negative 2x plus y equals negative 3. We let x be 0. We have negative 2 times 0 plus y equals negative 3. This term goes out, so y is negative 3. When x is 0, y is negative 3. So the point 0, negative 3 is on the graph, and that is our y-intercept. Let's go through the process of identifying intercepts using this equation. Now, the equation involves a radical, and as we set up our table of values, we might investigate more than just 2 points because the graph is going to be a curve and not a straight line, so we need a number of points to plot in order to discover the behavior of the graph. Also, we need to realize that in taking square root, we can only take the square root of positive numbers or 0 in the real number system. So we have sort of a limitation then on the domain here on the replacements of x. X can't be any less than negative 4. If it were negative 5, for example, negative 5 plus 4 would be a negative number. So that's out of the realm of possibility here. All right, let's go through the notion of making a table of values, and let's find our intercepts first. If we're looking for an x-intercept, then we would let y be 0 and solve for x. If we're looking for a y-intercept, we would let x be 0 and solve for y. All right, for the y-intercept, for the x-intercept, we let y be 0. What do we have here? We have 0 equals the square root of x plus 4. Now we have to solve this rascal. Well, let's see, squaring on both sides will undo this radical business. When we square over here, we get 0. When we square on the right, we get x plus 4. Subtracting 4 on both sides, we find negative 4 is equal to x. So when y is 0, x is negative 4, our x-intercept. For the y-intercept, let's see, we let x be 0 and we solve for y. If x is 0, we can just see right through this. If x is 0, this goes out, so we have the square root of 4 or 2. Let's plot those. We have negative 4 going to 0, so negative 1, 2, 3, 4 at 0, and then the point 0, 2. Now we need more information about the graph. We've already mentioned that we're not going to let x take on values that are less than negative 4, so that means that we won't have the graph. The graph won't make an appearance in this part of the coordinate plane, but it certainly makes an appearance over here. Now, let's plot points then in this interval, and we want to choose some points that are relatively easy to calculate. That is, we'd like to be able to take the square root of squares. And we don't absolutely have to do that because, after all, we have probably a calculator available to us, so we could approximate some values regardless of whether we're taking the square root of a square or not. But because we're doing this all by hand and we're trying to make life easy for ourselves, let's pick some easy values. Suppose I pick for x, let's say, we've already done 0. How about something like, negative 3? Because if x is negative 3, we have negative 3 plus 4, that's 1. The square root of 1 is 1. And that point is, let's see, negative 3, 1. All right. Good. Now what else? Let's see. I've taken the square root of 4. I've taken the square root of 1. I've taken the square root, okay, I've got another one could be that I'm choosing 5 for x, because 5 and 4 would be none. You see, that's the way you think through that. You want to think about values of x that will cause us to have a square in here. Okay, if x is 5, then we have 5 plus 4, 9, 3. So let's see, 1, 2, 3, 4, 5, 1, 2, 3. All right. Good. And the graph then looks about like this. And I want to go through here. And the graph stops right here. Let's take a moment here and look at the graph of this equation. Actually, we're going to pause and take a look at several graphs here, and we want to look at some of the features of the calculator as well. Notice that we are going to be using the TI-83 Plus graphing calculator to feature on this program. Sometimes we'll also be using the TI-83. Now, if you have a different calculator or a computer software program, feel free to use those. It turns out that all of these instruments have remarkably similar capabilities, and even if the button sequence on your calculator is a little different, if you just do a little pecking around, I'm sure you can find the sequence appropriate for your calculator. Well, we'll be using or looking at this particular shot many times on our program. This is the viewing window, and we'll be seeing it all of the time. We'll see the buttons below, so there'll be no confusion when I talk about pressing the window button and then entering a particular menu. However, the buttons below we haven't looked at, and if you're unfamiliar with the calculator, it might be important for us to just have a quick peek at those and survey them just a little bit as an introduction. I'm just going to slide the calculator up a little bit here so that we can see those buttons a little bit better. Now, the buttons that are in this region, these 2 rows along with these 4 buttons, are sometimes called editing features. The most important items are, first of all, these 4 buttons. When I say cursor up, down, left, or right, I'm talking about pressing these buttons. They just kind of move an icon around the screen. The next most important button probably is this one. This is the one that's pressed when we enter a variable into the calculator. It's marked x, t, theta, and n for various kinds of variables in different kinds of modes on the calculator. Now, these 2 buttons allow us to enter areas that are above and to the right or left of the buttons down here. If, for example, we want to press the square root button, well, the square root button isn't a main button on the calculator. It's called a second function. Now, notice it's color coordinated with the yellow up here. So these have a color coordination to them. If we wanted to find the square root of 20, for example, then we would want to access this button, and to do that it would be second and then press this button, and we are entering that item onto the calculator, and then we would enter 20 and then equals. But at any rate, so the second function will allow us to enter all of these items that are to the upper left of the buttons below. In a similar way, the alpha button allows us to enter the letters of the alphabet that appear above and to the right of various buttons down below. The D, for example, is the alpha key associated with this one. So when I say, if I would want us to enter D, I would say press alpha D. You see, and what I mean is press the alpha and the D associated with it below, like this. All right. Now, I mentioned that these are basically referred to as editing keys. A lot of times these are referred to as advanced function keys. Of course, the clear is not so much of an advanced function, but these certainly are. And we're going to learn about those and other aspects of the calculator on a need-to-know basis. Now, the buttons below this row are could be called just scientific keys, because they are the buttons that are remarkably similar to those that are found on a scientific calculator. Now, I'm just going to try to slide the calculator up a little bit here so that we can see many of these. All right, a number of things are kind of important to us here. First of all, notice that there are two things that look like minus signs here. Now, this is actually the subtraction symbol, and this is the negative of. And this button also corresponds to the sign change button on a scientific calculator. The enter button corresponds to the equal button on a scientific calculator. Now, all of the four functions, the four regular functions, are over here. Notice opening and closing parenthesis. We'll be using those from time to time. And a comma button here that's useful for certain purposes. Now, raising to exponents is accomplished in a couple of ways. If we're simply squaring, we can press this button. For example, 5 squared would be 5, and then press this button and then enter, and we would get 25 on display. Now, so this button will square anything that is on display. All right, now if you are raising to a higher power, you need to use this button. So when I say the exponent button, it is this one. You see, and sometimes this is called the hat key. But if we were squaring 5, it would be 5, and then press this button, and then a 2, and then enter, and that's 5 squared. Now, it's especially useful if we're raising, as I say, to a higher power. 8 cubed, for example, 8 hat 3, enter, that's 8 cubed. Okay, so that's the idea for the buttons that lie down in this region. Let's see, are there any others? I think that's about all that are in this area that we really need to be aware of right at the moment. Let's slide back down and actually enter some kind of equation. Now, you know, I mean, if I'm covering all the bases here, I need to say this, that in order to enter an equation onto the calculator, we need to write it in a particular form. Now, I'm going to just turn the calculator on, and you'll see some items here that I've entered using the alpha buttons. And the spacing was accomplished by using a space button in the alpha menu. And that space button is the alpha key on 0, if you're interested. But at any rate, if we have an equation written like this, in order to enter that equation into the calculator, we have to solve it for y. That is, we have to isolate y on one side of the equation. So to do that, we would add 2x on both sides, and that would give us this equation, and now we can enter it onto the calculator. Let's go ahead and do that. The equations are entered by pressing the y equals button, and then we could enter the 2x, whoops, only 1, 2, and the x, that's the variable key, and then minus 3, and now we're ready to go graph. Now let's just survey some buttons up here. The window button allows us to see the units that are designated for our viewing window. X minimum, -10, X max 10, same idea for the Y's. Now these are just horizontal distances, and these are vertical distances. The X scale I'll talk to you about in just a little bit. The zoom feature allows us to zoom in or out in various ways, and we'll also investigate these in just a little bit. But do notice that we can zoom in on a box that we create. We can zoom in at a point that we designate. We can zoom out from a point that we designate, and so on. The trace feature we'll look at in a little while. Here's the graph of the equation that we just entered. Now, let me show you the trace feature. If I press trace and press the left or right arrow button, then an icon will move along the graph. and the coordinates associated with that icon appear at the bottom of the screen. That's real nice, particularly if we're trying to find something like, oh, let's say the x-intercept. Well, let's see, now the x-intercept, you know, the place where the graph crosses the x-axis, has a y coordinate of 0. So we would be looking for a y of 0 as we cursor along. And gee, we can't land on a y of 0 here. And that's really because of the kind of setting that we're on right now. We just can't land on that point. But we can change settings and allow ourselves to land on that particular point. For this graph, it turns out that the value here is a friendly decimal. It's just a little short decimal number, and so we need to just change the one little feature on the calculator. I'll go to zoom, and I can do a couple of things. I can press either item 4 or item 5, I think, and accomplish this, but I'm sure I can accomplish it by pressing item 4. Item 4 is Z decimal. Now the graph comes up. I'm pressing trace, and I'll trace on over to that point. You see y is 0, and now I can read the x as the x-intercept. It is at 1.5. All right, just one of the little features about the calculator. We're going to have more to say about that Z decimal item in just a little bit. All right, now notice that, let me go back to the standard settings, the default settings. Now that's item number 6 here, and we can access that item either by cursoring to it and pressing enter, or by simply pressing number 6. So either way, we go back to our original feature. Now notice that the tick marks here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the left of the y-axis, and I have 10 to the right, and I have 10 above and 10 below. Well, that's because of the window settings that we have right here. So we can redesignate that if we want to. Now let's have a look at the scale situation. Back to the graph. Now notice that there are 10 tick marks in all directions. If I go back to window and set an X scale of, let's say, 2, and go back to the graph, go back to the graph, then notice that I have a tick mark at every other X unit left and right. Now the X scale on the Y-axis is still at 1. So that's what the X scale is all about. We can change it according to some kind of need a little bit later. Let's enter another equation. Suppose I go back to the Y equals menu, and I'll enter the equation that we were just discussing on the board a few moments ago. It's I'm pressing second and then square root, and remember it was the square root of x plus 4. So I'll press variable key and then plus and then 4 and then close parenthesis. Whoops, missed the 4. 4, close parenthesis. There we go. Now notice that the expression that appears under the radical needs to occur within a parenthesis here. On the TI-83 Plus, the opening of parenthesis is an automatic situation. On other calculators, it may not be. So make sure you have the item in parenthesis. Now I can press graph, and I have both graphs coming up on the screen at the same time. If I want to look at only one of them, I can go back to y equals, and I can deselect one of these graphs by cursoring left, and while the cursor is blinking on top of the equal sign, press enter. Now notice that what it does is it causes the equal sign not to be selected here. So I'm deselecting that equation for graphing. I go back to the graph, and I have the graph of only the one that is selected. So I can select, deselect as I see fit. Now let's go back and take off these equations. I'm pressing clear, cursor down, press clear, and now I just want to enter y equals x and look at its graph. Now we're on default settings, I think. Let me look at the window settings. Yeah, except for the scale. The scale is generally 1. But the graph, notice, is angled at a certain way through the coordinate plane. And this angle is a smaller one than that one. And if this is truly y equals x, then the angle right here should be 45 degrees. And the reason that it's not, the reason that the graph seems to be squunched down a little bit is that the default settings say for us to have the same distance left and right as we have up and down. You know, the x minimum and maximum are negative 10, 10, and for y, negative 10, 10. So that means a total distance here of 20 and a total distance here of 20. But the window that we're looking at is rectangular. So something sort of has to give here. If we're defining the same distance up and down as left and right, then we can think of what's happening here is that the graph is being squunched down a little bit like this, or the graph is being stretched like this. Either way you look at it, it's not a true square perspective. Now there is a button on the calculator that will automatically give a square perspective, but it's important that we be able to make the calculation ourselves. Let me show you an example. Suppose I go to the window setting and I set the y minimum at, let's say, negative 4 and the y max at 4. Now that gives us graphically a total vertical distance here of 8, because this distance is 4, that distance down here is also 4. So total distance of 8. Now clearly we don't have a square perspective. To create that square perspective, we take this distance and multiply it by 1.5. 1.5 times 8 is 12. So we want this total distance to be 12. Okay, let's set that up. Now if we'd like that distance to be 12 and we want half of the distance on this side of the y-axis and the other half over here, then we're going to set our x minimum at negative 6 and our x max at 6. Let's go to the window settings and do that. So negative 6 for the x minimum, 6 for the x max, and here's the graph. Oh, that's nice. There's a square perspective. There's just one other topic I want to return to briefly, and it has to do with friendly settings. Friendly settings are settings on the calculator that will allow us to trace left and right and have relatively simple decimals for coordinates of points. Now here I just press trace, and as I trace over to the right, notice that the values for x and y are not very friendly. They're not very nice little decimals. Now I can accomplish friendly values by going to the zoom menu and pressing Z decimal. That's kind of an automatic way to do things. But we ought to be able to make the calculation ourselves. Now notice when I press trace and tracing to the right, I get rather simple decimals here. Now we need to be able to make the calculation ourselves because it's not always the case that we want this particular window setting. You see, we might want to make this friendly value setting when we are looking at a graph way over to the right or way over to the left or something like that. Now the settings that give friendly values like this are related to the number of pixels left and right on the screen. There are 95 of them, and therefore there are 94 steps required to step on all of them. If you're on the first one over here, then you would have to step 1, 2, 3, 4, 5, and so on all the way to 94 in order to step on the 95th pixel. Now that's related to the calculation of that total horizontal distance for friendly values. Now let me go back to the window setting, and I said there are 94 steps. Well, suppose I take half of 94. That's 47, and I set this at negative 47 and then this at 47. All right, now I'm not going to change my y distance here, so the graph is going to look pretty skewed, but the graph then looks like this, and on trace, notice what happens. I have integer values for x and y. Now it's the x that I'm more concerned with here, though for a different graph the y value might be some kind of decimal value. But it's the x that is an integer because we made those particular window settings. And it turns out that the 94 is a rather magical number. If we take the 94 and take an integer multiple or integer divisor of 94, we will get relatively friendly values. And that's why the negative 4.7 works so well, because we're simply dividing by 10, you see, and we're getting a close-up view and also arriving at friendly settings. Now we can do the same thing by just doubling these amounts. If I just take, well, up here, if I just do this, now I'm just going to go times 2, all right, and then I'll cursor down and it'll automatically make the calculation for me. Now times 2, all right, and now I'll go to the graph And we don't have a square perspective, but no matter, we're after the friendly settings here. And now I just cursor to the right. Notice, once again, we have friendly settings, and it's because of that idea of that total horizontal distance of 94 or 9.4 and integer multiples or divisors of those. One of the things that we'd like to be able to do throughout this course from time to time is be able to recognize a graph or construct a graph just by looking at an equation. It's quite an interesting technique. We have to study the relationship between graphs and equations quite a bit to be able to do that. Now, and also that's quite a difference from using the point plotting method to generate graphs. Well, one very recognizable graph from its equation is the circle. And let's develop the relationship like this. Consider this circle whose center is at 3, 4. Now, if we just count out from the center to the outer edge, we'll have the radius of the circle. It's 1, 2, 3, 4, 5, 6. Okay, so we have a radius of 6. And therefore, this distance is 6. Now, we're going to actually develop the equation related to this circle. And it's not too difficult to sort of conceptualize how we're going to do that, because circles are defined as all the points in a plane that are the same distance from a center point. So we're going to use our distance formula for this purpose. Now, consider that this point to the edge of the circle is a general xy value. And now let's begin the process of developing the equation associated with this by just taking our distance formula and putting in information that we know. Now, the distance that we're talking about is 6, and it's distance from this point to the edge of the circle. All right, the points on the edge of the circle are kind of general xy pairs, but the point in the center is a specific 3, 4. Now, when we talk about difference in x components here, one of these x components, one of these horizontal distances, is the x associated with the point on the edge of the circle, and the other is the point at the center. So one of these x's is 3, you see, because of the coordinates of this point. All right, so it's x minus 3 squared, and then a general y minus the y component for the center, 4. And so we have this equation. Let's manipulate it a little bit. Squaring on both sides will clear the radical, so we have 6 squared is equal to this. Now, when this equation is used, and when we're trying to recognize a graph from an equation in this situation, a lot of times this information is listed on the left side of the equation. So let's just swap sides. All right, so now we have this. Now, notice that the 3 and the 4 are the coordinates of the center of the circle, and that 6 is the radius of the circle. We can generalize this situation like this. We can say, okay, let's just let letters stand in for 3 and 4. Now, not x and y here. We want some foreign letters like h and k. All right, so I'll let this, the x component for the center be h, and the y component for the center be k. And we'll let r stand in for the 6. And now we have a generalized version of what we have up here, and if we can write an equation, or if we can see it in this form, then we can easily identify the position of the center, the coordinates of the center, and they would be h, k, and the radius would be r. All right, now, one thing to notice here that's really important is that h and k are numbers that follow minus signs. That's really important, because if we have a plus sign in here, we have to create a situation where the number follows a minus sign in order to be able to see the coordinates of points, of that center point. Consider a circle whose center is at 2, -1, and whose radius is 4. Let's build the equation associated with this, this information. Now, we start like this. We think, well, let's see, the equation of a circle has the form of x minus h squared plus y minus k squared equals r squared. And then fill in the information that we see. Well, let's see, we see x minus the h and k now, coordinates of the center. So the h is 2 and the k is -1. So x minus 2 squared plus y minus -1 squared equals 4 squared. We would probably clean this up a little bit. X minus 2 squared plus y plus 1 squared equals 16. Now, sometimes the equations come to us like this, and we're asked to give information like that about its graph. And we could certainly see through this. Now, the number that follows a minus sign here is 2. But here we would have to actively think about kind of backtracking here and putting the equation back into this form in order to see the y-coordinate for the center. And similar idea for the radius. A lot of times the amount that's squared is what we're looking for, but the amount that's squared isn't evident here until we rewrite it in a form like this. All right, so that's the idea. Suppose we have this information. Suppose we know that the center is at 3, -2, and a solution point to the equation that we're developing is -1, 1. Well, we would certainly start the same way. We would start with the sort of the format or the template for the equation associated with a circle. Let's talk about solution point just a minute, though, because we're going to come back to that in just a second. A solution point means an XY pair that solves the equation that we are developing. Now, what does that mean graphically? Well, graphically, we know that solution points are points on the graph. So this is nothing more than a point that's on that circle that we're trying to find here, find information about. And actually, we could plot this point, we could plot that point, we could find the distance between these two, we would have the radius of the circle by finding that distance. But I think we can be a little more clever about finding that distance. Let me show you what I mean. We start out with this. Now, we replace within this format the information that we know. We know this 3, -2 is the h and the k. So we have the 3 and the -2 here. We would clean this up as y plus 2 all squared. Okay, now we're at a point where we need r. Now, again, we could find r, we could find that radius by just finding the distance between those 2 points, that is, using the distance formula. But there's another clever way to do that. We know that every point on a graph is a solution point. It solves the equation. It makes the equation associated with the graph true. And so this XY pair makes this equation associated with the graph true. So let's use that information. This is just an x and a y value. So let's see if x is replaced with -1 and y is replaced with 1. We have truth in our equation, and therefore we can solve for r, you see. All right, -1 minus 3, that's -4 squared is 16. 1 plus 2 is 3 squared is 9, is r squared, so 25 is r squared. R then is going to be 5. Now, if r is 5, we can put that information back into this form of our equation, and we've got the equation that we're looking for. And it's complete. I'm erasing this because I'm going to come down here with some more stuff in a second. But we have x minus 3 squared then plus y plus 2 squared is 5 squared. Okay. Now, this equation is an equation which is in standard form. We call it standard form. There are 2 forms to equations that are important to us. One is called standard form, the other is general form. The standard form of an equation is a form which gives us information about the graph of the equation. The general form is an expanded form of the equation. The general form associated with this one would mean, well, let's see, let's square here and go ahead and square there. You see, just expand it out, perform the indicated operations. Now, this would end up being x squared minus 6x plus 9, and then y squared plus 4y plus 4 equals 25. And then we could throw all the terms on one side, rearrange a little bit. We could have the terms that are squared written first, kind of like this, and then minus 6x, and then plus 4y, and then the 9 and the 4, that's 13. But if we move the 25 over to the left, we'd get negative 12 equals 0. So here's the general form of the same equation. Now, there must be a way for us to take this general form of the equation and move back into a standard form in order for us to understand aspects of the graph and to see those aspects of the graph. And certainly that's the next thing that we want to do. Certainly we ought to be able to do that, and it's not too difficult. Let's go through the process. Here's the same equation, and I want to work back the other way, and here's how we proceed. We put the terms involving x next to one another. We leave a space, put the terms involving y next to one another, leave a space, put our equal sign, and kick the constant to the other side. We're adding 12 on both sides to get this. All right, here's how we're thinking about the problem. We're thinking, okay, here are our terms involving x. Here are our terms involving y, and there's our constant. Now, what we intend to do is create a situation here where we invent a constant which will allow us to factor into a binomial squared. Now, we're trying to create then a trinomial square. And by the way, this is called, the process is called completing the square. You may recall it from another situation. But to complete the square here, we take half of 6, that's 3. 3 squared is 9, so I'm adding 9 here. But if I add 9 here, to maintain the balance of the equation, I need to go over here and add 9 as well. Now, let me continue this one step further, and then I'll address this situation. But factoring here, we get x minus 3 squared. And then over here, we'll do the same kind of thing. We'll complete the square. We're completing the trinomial square. Half of 4 is 2. 2 squared is 4. Add 4 here. To maintain the balance, we add 4 on the other side. And now factoring, we get y plus 2 squared. And on the right, we get 25 as expected. Now, we can recognize then the aspects of the graph that we're looking for. We're looking for the center. You could see the center at HK. Now remember, H and K have to both follow minus signs. That one doesn't. So we have to think of this as minus negative 2. So our coordinates are 3, negative 2, and we have a radius of 5 as expected. In an earlier segment, we talked about x-intercepts and y-intercepts, and those were intersection points of graphs with the x and y axes. Well, here we're going to talk about another kind of intersection point, and it is the intersection point or points for two different graphs. Suppose we have a couple of graphs here, and now one of these, the curve here, the parabolic curve, is the graph of y equals x squared minus 3, and the straight line is the graph of y equals x minus 1. In some business applications, and we'll see a couple of examples in a minute, it's important for us to identify points of intersection of a couple of graphs. And here, all we're doing is identifying these 2 points of intersection. Now, we can identify those points both graphically and algebraically. And you've probably seen it in the past, I'm sure. And here it's pretty easy graphically to identify the points. We have a point of intersection here at 2, 1. And another over here at, let's see, negative 1, negative 2. Now, I say it's pretty easy graphically in this problem, but in real life, it's often the case that very large numbers are involved, and a little point on a graph, you see, is very difficult to determine exactly the values that will give that intersection point. So we need to resort to some algebraic method for making the calculation. Now, the algebraic methods, there are a couple of them. The easiest way here, though, is to use substitution. Now, notice the equations for the graphs are written in the form y equals. And one of the methods that you studied before is the method of substitution, and substitution means that you solve one of the equations for one of the variables and then take that information and put it into the other equation. Well, both of these equations are solved for y. That is, they're written in the form y equals. So the substitution idea is particularly easy. If we just take this expression for that y and replace the y in this equation with that expression, you see, then we will find the value of x that will be the intersection point. Here's what I mean. I'm replacing this y with this, and so I've got x squared minus 3 equals x minus 1. And I go through and solve this. Well, let's see, I need all the terms on one side. It's a quadratic equation, so I'm going to try to solve by factoring. I've got x squared here. When I subtract x on both sides, I get this. When I add 1 on both sides, I get minus 2 on the left, and on the right I have 0. Now factoring, I get x minus 2 times x plus 1. And then the values of x that are the zeros for the factors are x equals 2 and x equals negative 1. Now these values don't give me the coordinates of the point of intersection, but they are the x components for those coordinates. And to find the y values associated with these x's, we simply take these values of x and replace within either of the original equations. Now if I take x and replace x equals 2 with this, you see, then y is 2 minus 1. Oh, that's 1. So when x is 2, y is 1. So the point 2, 1 is an intersection point. And in a similar way, if I replace x with negative 1 here, negative 1 minus 1, oh, that's negative 2. So when x is negative 1, y is negative 2. And sure enough, those are the intersection points that we found up here. All right, so that's the sort of the math behind a real-life situation illustrated in this problem. The problem says, a business manufactures a product at a cost of 65 cents per unit and sells the product for $1.20 per unit. The company's initial investment to produce the product was $10,000. How many units must the company sell to break even? Now we're trying to find a break-even point, and in doing this, it's valuable to identify a cost and a revenue equation, and it's pretty easy to do in this problem. For the cost, it tells us that the company's initial investment to produce the product is $10,000, and then each unit will cost a certain amount after that, and it's 65 cents per unit. So the cost equation, or the cost function, is the $10,000 initial investment plus 65 cents per unit. And x is the number of units here. Now there's a revenue equation that can be generated here, and it comes from the sales of the product, or $1.20 per unit. So gee, the revenue equation is $1.20 times x number of units, or 1.2x. So fairly simple. They're both linear here. And if we take this cost equation and this revenue equation and we construct the graphs of these two, then we get a graph that looks like this. Now, notice that here we have the revenue graph and the graph for the cost. And we'd like the break-even point. Well, the break-even point is just the point of intersection of these two graphs. Now, notice that along this axis is some number of sales, and the number of sales is in thousands of dollars. And here we have some number of units, you see, and that also is in thousands. Now, by the way, to construct the graph, if you're using the point plotting method, I just made a little table of values here and plotted a bunch of points and then drew the graph as we are accustomed to doing. But in each of the two little equations, you just replace x with, and I replaced x with 5,000, 10,000, 15,000, and so on, and plotted some points. Okay, and when I replace x with 5,000, 10,000, and so on, you get a value for cost, a value for revenue in the other equation. All right, so that's how the graphs came about. Now we'd like to identify this point of intersection, and we can kind of estimate it here by looking at the graph. Let's see, the number of units is, and I'm just kind of looking under here, it looks like it's about, well, it's just under 20,000 units. But gee, I can't tell exactly how many. And I can also calculate the number of sales that would occur at that break-even point, you see, by looking up on the y-axis. Well, to find the exact break-even point, I would need to use an algebraic method. And the method looks like this. Here are our two equations. Now, the top one is the cost equation, and the bottom one is the revenue equation. And I'm solving in the same way that I did before, by substitution, because it's just the easiest way here. By the way, another algebraic method was the method of elimination, when you solve systems of equations, just to remind you of that. But the substitution method is real easy here. If I take this expression for y and replace it into the other equation, then I get this, and then I'll subtract 65/100ths x on both sides to give this, and collecting I get 0.55x. Dividing on both sides by 55/100ths, I find x to be about 18,182 units. Now, that's the number of units, you see, that has to be produced and sold in order to have a break-even situation. Now, people running the company would want to analyze this sort of thing, and an interpretation can also be made in other parts of the graph. So here is the spot where that many units are sold. We could plug a number of units, by the way, into either of the two equations to find out the amount of money in sales that would be generated at that break-even point. But we're not going to do that here. Here's a rather interesting situation, though. For other values, for other numbers of units, we can actually see some amount of loss or profit in different areas of the coordinate plane. For example, at 5,000 units. Now, here's revenue. So the revenue is this much, you see, and the cost is this much. So if we're bringing in this amount of money and it's costing us this amount of money, the difference here would be the amount of loss. So that then would be the amount of loss if we are producing 5,000 units. And on the other hand, we can come up here and say, well, gee, if we can produce 30,000 units, what will our profit be? Well, the profit is the difference between the cost and the revenue. You see, so we have cost up to here, we have revenue up to here, and that difference turns out to be the profit. So we can make that kind of interpretation with a graph like this. Here's another situation involving an intersection point. It has to do with supply and demand. Now, a great deal of study is involved with the notion of supply curves and demand curves and that kind of thing. And let me give an interpretation here of why the demand curve seems to be falling and the supply curve seems to be rising. First, look at the different axes. Here we have price, and here we have number of units. Now we're going to come up with a specific problem here, and so the number of units is going to be in millions. But just for the time being, number of units and price. Now think about demand, and then we'll think about supply. Let's talk about demand. Does it make some sense that if the price of something is very high, that you're not going to be able to sell very many of them? You know, if a lawnmower was $5,000, you see, and other lawnmowers are out there for $200, let's say, then you're not going to sell very many at $5,000. So that's kind of what this is all about, that if the price is high, you're not going to sell very many, you see. And as the price falls, you sell more of those rascals. So if the price gets really low, then you're going to sell more and more and more. So that's the idea. So that's the demand curve. Now, on the supply side, this is production. We can think of it like this is production. And so as we produce more and more items, the cost of that production is just rising. You see, if you produce an awful lot of things, then the cost of that production goes up, up, up. All right, so supply and demand curves. Now, the point of intersection of the supply curve and the demand curve is called the point of equilibrium. And this is a point around which companies would like to conduct their business. They would like to not have too much on the supply side. They don't want to be too far on this side either. They would like to be conducting business in a particular range or interval around that point of equilibrium. So it's important for them to identify that point of equilibrium if they can generate equations for supply and demand. They're not real easy to generate, and you'll know a great deal more about this, I'm sure, from the other courses that you take. Because if you're in this course, then you're probably also studying some things about the supply and demand idea. And your professors are going to tell you a great deal more about it than I do here. I'm just painting with a broad brush. But the notion here is that we're looking for that point of equilibrium, which is that, that point of intersection. And if we have equations which are associated with these, and again, they are a lot of times very complicated to generate equations for each of these. But let's say that concerning DVD players, that we have a price on the supply side of 195 minus 5.8x. And on the demand curve is 150 plus 3.2x. And to find the point of equilibrium, we would do just like we did before. You see, we would set the two equations equal to one another, or the two expressions equal to one another, solve for x. And then we could plug that value of x back into either equation and find the value for the price associated with that number of units, x. And it turns out that the number of units, x, is 5 for these two. And remember, that's in millions, so it's 5 million units would give us a point of equilibrium. And it turns out that the price at for 5 million units is $160. Excuse me, $166. So there's our point of equilibrium. One of the most important things we do in math is conjure up equations that help us solve word problems. And sometimes the equation is nothing more than a formula that we bring to bear onto the word problem, and other times we have to make up the equation ourselves according to the nature of the problem. I think one of the most intriguing ways, though, that a mathematical model can emerge is from raw information, and that occurs in this problem. It says the amount of money Y in millions of dollars spent on college textbooks in the United States in the years 1993 to 1997 is shown in the table. Now here's the table. So in the year 1993, this many millions of dollars were spent on textbooks. And in 94, this number, 95, 96, 97. Now, it turns out that we can go through a process of developing an equation whose graph best fits this information. And here's that mathematical model. Here's that equation. Now, there's a lot that happens between here and here, though, and we want to talk about that a little bit. I want to tell you how this equation emerges, and it's all done on the calculator. We don't have very much to do. It's very complicated, though. If you look at the algebra behind it, it's a little bit complicated, but for the calculator, it's really a cakewalk. Now, I'm going to show you the button sequence necessary in doing this, and I'm going to tell you how important it is in a problem like this, because you see, what we're doing is we're looking at these pairs of numbers. 1993 is associated with this. 94 is associated with this. So all we have is a bunch of ordered pairs of numbers. Now, this ordered pair situation allows us to graph. You see, we can graph the pair 1993 and 2493. All right, that's just the coordinates of a point on a coordinate plane, and here are the coordinates of another point, and another, and another, and another. And gee, if we plot those points, you see, then a pattern emerges. And then we want the equation whose graph goes through those points on that scatter plot, it's called. Well, we think of the situation like this. We think of the ordered pairs of numbers more like this than a table like the one that we just saw. And as a matter of fact, if we're thinking about pairs of numbers, since all of these start with 199, you see, then we can just take the last digit. We can say 3 is associated with that number, 4 with that number, 5 with that number, and so on. And we just understand that 3 means 1993, and 4 means 1994, and so on. Okay, now here's how we enter the information in the calculator for the calculator to first make the stat plot. We're going to make the stat plot and just talk about how that's done. And we're going to also come up with that mathematical model that we saw. If you press Stat and then select item number 1, Edit, then a couple of tables emerge. And the tables at the top, if you're on the default settings, are labeled L1 and L2. So in list number 1, put the first items in these ordered pairs. Put the 3, 4, 5, and so on. Just enter those all the way down. And then slide over to the right, use the right arrow button, slide over to the right, and under L2, put the numbers associated with the ones on the left. Okay, so now you have the ordered pairs listed. That's the most difficult part. There's nothing really difficult about this from here. It's just knowing where to find the right buttons on the calculator. The calculator is doing all of the work. All right, we want to make the calculator give us the stat plot. And here's what you do. Second y equals. Now, the second function on y equals is marked stat plot on the calculator. Press enter. And what you want to do is turn the plot on. So you select, use the cursor to put the icon on top of the on button, press enter. And now you want an appropriate window setting, and again, the calculator can do this automatically. Press the zoom button and select item number 9, which is zoom stat. All right, now, once you do that, the calculator will go into the stat plot. You will see the points that we have entered here on the coordinate plane. Okay, great. Now what we'd like to do is calculate that mathematical model. That model is called a regression equation. And it's because the process within the calculator is called a least squares regression. So it's a regression equation. And here's how you make the calculator make that calculation. You press stat, and then you slide over, and I think what you do to select calc is you press the right arrow button. This is one of the items at the very top of the menu. So calc for calculation. Now, what we're calculating is a regression equation. You'll see a whole bunch of them listed there. You'll see a linear regression and a quadratic regression, and we're going to select cubic regression. Now, why are we selecting cubic regression? Well, it's because of the nature of the pattern of the stat plot. You notice on the stat plot that there are actually 2 curves going on, and at the bottom of the group, you have a curve that it kind of curves up like this. And then at the top, it's kind of topping out at the top. So with 2 curves, a cubic regression might be the best fit. On other situations, you might see different kinds of patterns emerge, and experience would tell you which regression model might fit best. A logistics model might fit well on this one as well. But at any rate, we're selecting item 6, cubic regression. Press enter and then enter again, and all of the information about this cubic function comes up. The general form of the cubic function shows up, where it's ax cubed plus bx plus c, ax cubed plus bx squared plus cx plus d. And the values for a, b, c, and d are listed there. Those are the coefficients and the constant involved in that function. And so we have our function. Now notice all of those, the value of a, b, c, and d are big, long-winded decimals. You see, now we could take those values and we could put them into the place where we're going to enter the equation for graphing. We could do that ourselves. We could write them down on another sheet of paper and put them in by hand if we want to. But do we want to do that? No, we want the calculator to do that. And here's how we make the calculator do it. We press y equals. Now, when you press y equals, if there are no other functions on board, then the blinking icon is to the right of y1. All right? And with the blinking icon in that spot, press the button marked VARS. And by the way, all of these button sequences are for the TI-83 Plus. And there are equivalent button sequences for other calculators. All graphing calculators pretty much can do this same kind of thing. But VARS. And then select item number 5 for statistics. And then you'll need to slide over because you want the top of the menu to be EQ, equation. You see, and to get to equation, I think it's 2 right arrow pushes to get to equation. And under equation, the very first item is the regression equation. Press that button, press enter there, and you'll see that all of this great big elaborate complicated equation comes on to where y equals is located. And now just press graph, and you see the graph will overlay right on top of the stat plot. It's a pretty good fit, isn't it? You see that the graph goes through all of those points. Now why are we doing all of this? What value does this have? Well, this model allows us to make the calculation for textbook expenses in some future year. If you want to find out or estimate what the cost or the expenses for textbooks will be in some future year, then what you can do is either use the model algebraically, just write down the model and replace t in the model with some amount of time. Now remember, t stands for some year. It's the last digit in a year. And if you want something like, now remember, the 3 would stand for 1993. 5 for 1995, and so on. So if you want something in like the year 2005, then you have to make an adjustment there. You have to say, well, gee, from the 1995 would be 15 years after the year 0. The year 0 corresponds with 1990 because the year 3 is 1993. I don't want to make this too complicated, but that's about what it amounts to. So the year 0 is 1990, so the year 2005 would be 15 years from 1990, and therefore you would enter 15 for the value of t. Plug it into the model and you'll find out the amount of money spent in that year, or you'll be estimating it. Now, but there's an even easier way to do it. Just use the calculator. We can jump onto the graph and we can use the trace feature, you see. Just trace over to a t of 15 and it'll give you that value. Now you may have to change the window setting a little bit. It may be off screen just a little bit to the right, but it's an easy adjustment. Okay, now related to this idea of regression equations would be all of the models, the regression models that are available. And you've studied these kinds of things before, but I just want to refresh your memory a little bit that it's helpful for us to know the basic patterns of some degenerate families of functions. And it just helps us understand the kind of function that we may be dealing with in certain situations. A linear model has a graph which is a straight line. This is the graph of y equals x. The degenerate quadratic model is y equals x squared, and it has one curve in it. That's kind of an important idea. If your stat plot just has one curve, you see you might have points that are where I'm putting my finger here, just one curve, then gee, you might use the quadratic model to emulate that situation. The cubic model is what we use, and the cubic model, the characteristic is that there are two curves in it. Now those curves may not be located exactly like this. They may be in other places on the graph, as we saw earlier, but there are two curves involved. Y equals x cubed is the graph that we see here, the cubic model. The square root model kind of has this behavior. The absolute value model tends to come to a point and then go off in another direction. And this is the graph of y equals the absolute value of x. And the rational model looks something like this. This is the graph of y equals 1 over x.